Welcome to Maths with EJD. In this video, we're looking at the Sturm-Liouville problem, and it's coming right here because we've been talking about boundary value problems, which Sturm-Liouville problems actually fit into this, although it's difficult to actually consider them as numerical analysis issues or something. But I mean, I just feel it should come up right here. So let's embark on this journey. And of course, we always we'll end it with the Python implementation to see the beauty of the Sturm-Liouville problem. So let's have an overview. Let's have an overview of the Sturm-Liouville problem. Overview. The Sturm-Liouville problem is a class of second order linear differential equations with boundary conditions. These problems typically involve finding eigenvalues. Interestingly, we're back to eigenvalues and eigenvectors. I had a sub series on in this playlist where we are talking about eigenvalues and eigenvectors all the way, and we saw some of the applications. So this here again we have this under boundary value problem. So these problems typically involve finding eigenvalues and eigenfunctions, or what you can call, which may be analogous to eigenvectors, right? And eigenfunctions that satisfy certain properties, such as orthogonality, orthogonality, and completeness. Okay, so the the general form of a Sturm-Liouville problem, of a Sturm-Liouville problem is d dx of px dy dx plus q of x y equals lambda rx y. So that's the typical Sturm-Liouville problem. This is what it looks like. This is what the typical Sturm-Liouville problem looks like. Okay, where y of x, for this y now, where y of x is the unknown function we are looking for. You know, when we solve a differential equation, we are looking for the result is a function. So y of x is the unknown function. That is the eigenfunction, Then we have p of x, q of x, and r of x are functions that are given functions. Of course, as we always know, lambda is the eigenvalue. Lambda is the eigenvalue. Then we have boundary conditions. Boundary conditions are provided boundary conditions are provided at the endpoints. At the end points, x equals a and x equals b, like that. So let's take an example and see how this goes. So let's solve the following simple Sturm-Liouville problem. Which is minus d squared y dx squared equals lambda y, where 0 is less than x is less than pi. And then we have y of 0 equals 0 and y of pi equals 0 also. I think it bears close resemblance with what we did when we were talking about shooting method. So it's important to know that this problem, this equation, that is, this equation corresponds to a specific case, where, now if you compare this with the regular Sturm-Liouville problem, right? This is d squared y dx squared. That's like d dx of, that's like d dx of 1 dy dx or something like that. So, so if you look at this, right, it looks like we have, okay, let me even try to write it that way. So this is minus d squared y dx squared equals lambda y. Then if you're following the Sturm-Liouville pattern, it means that we have d dx of p of x dy dx. So this is more like, okay, this is not negative. This is not minus, I think. This is not minus. I think this is not minus. Yeah, this is not minus. Okay. So from the look of things here, right, this is basically the same thing as d dx into dy dx. Okay. And that is equal to lambda y. So if we want to make it look like the proper Sturm-Liouville, so normally it should be d dx into p of x times dy dx. So if dy dx is the only thing we have here, so that means that we have d dx into 1 times dy dx. So meaning that our p of x now is equal to 1. Then if you also come here, we have plus q of xy, and there's nothing like q of xy here. So there's nothing like q of xy, so we have plus 0 times y, okay, equals the right-hand side, which is lambda r of x, y. So, and on that side, we have lambda y. So it means we have lambda times 1 times y. So in essence, we are saying that p of x equals 1, q of x equals 0. That is this, and then r of x is also equal to 1. That is this now. So it's more like the Sturm-Liouville problem with those particular situations. That's why we said this equation corresponds to a specific case um where again p of x is 1, q of x is 0, and r of x is also 1. R of x is also 1. Okay. So okay. Now I'm going back and forth. This is actually minus, sorry. This is, but I mean, with the minus, right? This actually, with the minus, right? Even with the minus, it's simply, okay. With the minus, it simplifies to d squared y dx squared plus lambda y. If you transfer this one here, it will be minus d squared y dx squared minus lambda y. But if you take away if you multiply through by minus, you end up getting all this to be equal to 0, like this. So this is another way to have it. So the minus is part of it. Sorry for the back and forth. Okay, now that that is settled, let's solve the differential equation, right? So first step 1, solve the differential equation. Solve the differential equation. So the solution to the equation, that's what I'm saying. This may not really look like numeric like that. D squared y dx squared plus lambda y equals 0 depends, it actually depends on the value of lambda. So we have like 3 cases. So for case 1, if lambda is greater than 0, so in that case we say let k be equal to square root of lambda. So the general solution is y of x equals a cos kx plus b sine kx. So that is one possibility right there. Then we can have case 2. So it depends on the value of lambda, like we said. If lambda is greater than 0, we can have what we just had. Then we can have case 2, where lambda is equal to 0. So in that case, the solution would be y of x equals a plus bx if lambda is equal to 0. So this is the second possibility we have for that. And we have case 3. We have case 3. If lambda is negative, lambda is equal to 0, is less than 0. So in that case, we say let lambda be equal to minus k squared, and the solution becomes y of x equals ae raised to power kx plus be raised to power minus kx. So this is yet another solution depending on the sign of lambda. Now, with all of this out of the way, okay, well, I mean, still talking about this. So in this case, right, in this case, we focus, okay, let me just, it's more like an overall thing. So in this case, we focus on case 1, where lambda is greater than 0, where lambda is greater than 0, and thus the solution is y of x equals a cos kx plus b sine kx. So that's what we settle for. Now, that is step 1 done. So let's go for step 2. Step 2, we apply boundary conditions. Apply boundary conditions. That's step 2. Apply boundary conditions. So first, we know that at x equals 0, y of 0 is equal to 0. That's one thing. So that means that y of 0, that's from this expression now. Y of 0 is equal to a cos 0 plus b sine 0. Of course, sine 0 is 0, cos 0 is 1. So that tells us that, of course, and this, so that means that y of 0 is equal to a. Y of 0 is equal to a. And since y of 0 is 0 already, so that implies that a equals y of 0, and that is equal to 0. So we see that a is equal to 0. And the solution, simplifies, to y of x equals b sine kx. Okay, we have this. Now that's the first boundary condition, I believe. What about the other one? We say number 2, at x equals pi. Now that's the other end. At x equals pi, we have that y of pi again is still 0. Okay, so this gives that y of pi is simply equal to b sine k pi, So we now say for non-trivial solutions, that's solutions that are not 0. So for non-trivial solutions where b is not equal to 0, we must have that sine k pi is equal to 0. So what that simply means is that which implies that k is equal to n, where n is a positive integer. N is a positive integer. So thus k equals n, and the eigenvalues are lambda n, which is equal to k squared. Don't forget where we are coming from. The answer we are settling for is this one, that lambda is greater than 0. So k is greater than lambda. So that means that lambda is k squared. Okay, since that's where we're coming from. So lambda n is k squared. And since k is n, so we have n squared. And n starts from 1. So we have n is 1, 2, 3, and so on and so forth. Okay, we have this now. So these are the eigenvalues. And we go for step 3. Step 3, we talk about the eigenfunctions, and eigenvalues. Okay, so we say for each eigenvalue, lambda n equals n squared, the corresponding eigenfunction is yn of x, which is equal to b sine nx. And with that, we have lambda n equals n squared, with n equals 1, 2, 3, like we saw the other time. So it's like we have the complete set with this now. So we have this now. But then we can still say something else. The constant b, this one, can be chosen arbitrarily. So we typically normalize the eigenfunctions. the eigenfunctions by setting b equals 1 for simplicity. Okay. So that leads us to the idea of orthogonality of eigenfunctions. Orthogonality, that's step 4 now. Step 4, orthogonality of eigenfunctions. So the eigenfunctions corresponding to different eigenvalues are actually orthogonal. They're orthogonal. To demonstrate this, consider the inner product of two eigenfunctions. That's ym of x equals sine m of x and yn of x equals sine nx rather on the interval 0 comma pi. So then we have integral from 0 to pi of ym of x multiplied by yn of x dx, which is equal to integral from 0 to pi of sine mx sine nx dx. So using the trigonometric identity, I think I've done something like this on that trig. I have a playlist on trig, so you want to check that out. Using the trigonometric identity, we now have sine mx sine nx equals 1 over 2 into cos m minus n x, then minus cos m plus n x, like this. The integral becomes integral from 0 to pi of sine mx sine nx dx equals 1 over 2 integral from 0 to pi of cos m minus n x dx minus integral from 0 to pi of cos m plus n x dx, like that. So both integrals evaluate to 0 unless m is equal to n. So we get So we now get integral from 0 to pi of sine, integral from 0 to pi of sine mx sine nx dx is equal to 0 for m not equal to n. Thus, the eigenfunctions, thus the eigenfunctions yn of x is equal to sine nx are orthogonal. They are orthogonal, orthogonal on the interval, on the interval 0 to pi. So in conclusion, yeah, I think this is important to note. So in conclusion, right, we have the following. In this solution, to the Sturm-Liouville problem, to the Sturm-Liouville problem, first point, the eigenvalues are lambda n equals n squared, where n is equal to 1, 2, 3, and so on and so forth. Then the next one, the corresponding eigenfunctions. The corresponding eigenfunctions are yn of x equals sine nx. Okay, then we have the next, the eigenfunctions are orthogonal with respect to the inner product, that's integral from 0 to pi of ym x yn of x dx. And lastly, the eigenfunctions form a complete set, allowing for expansion in terms of these functions. Okay. Yeah, as usual, let's see the Python implementation. It shows a very beautiful story of this. Okay, so I mean in line 1 and 2, we see that we need numpy and matplotlib. Then line 5, we discretize the interval 0 to pi into 500 equal parts. Then in line 8, the number of eigenfunctions we are looking for is 5. Okay. So we are that's like we are defining the number of eigenfunctions to compute. We can do more than that for sure, but because we have 1, 2 upwards. So function to calculate the eigenfunctions for the Sturm-Liouville problem. So you have defined the eigenfunctions. We know the eigenvalue, the eigenfunctions are actually sine nx with n starting from 1 upwards. And we define the orthogonality, which we say n period traps, that's from numpy. And we have the eigenfunctions multiplied by the transpose of the eigenfunctions. That's the idea of orthogonality, right? Then we, of course, all these are just to define how the graphics will look like. So the plot of the graphics and all of that. So, I mean, you can study this better. If you're on Facebook, you can find the code right there. Just copy it out, put it on Jupyter Notebook or whatever IDE you have, and then run it and play with it and see what happens. So if I run this now, you have something very beautiful spewing out. So we are computing from n equals 1 to n equals 5. So you can see the eigenfunctions, how they go. So you see this is for n equals 1, followed by n equals 2, which is I think this orange. Yeah. So that's like, so you have this one. So this is 1, 2 turns like that. So for green, 3, that's 1, 2, 3. So you can see it follows the numbers. Then for the red one, you have 1, 2, 3, 4, like that. Then n equals 5. It keeps going like that. So if I increase the number of eigenfunctions, say I want like 10. So we're going to have 10 functions like that. So you see it's more serious like this. What if I even want to do, I mean, we also have the orthogonality matrix of the eigenfunctions displayed down here, and then with all the corresponding um, orthogonality matrix. So you can, I mean, we can go. If I do 100, I mean, I don't know. I just want to see that's going to take a bit of time. So, okay, now it's not making too much sense because it's just too much. So let me do 20 and see what happens. So you can start from n equals, and so it becomes like this. Yeah, still a bit beautiful, showing some nice pattern. So, I mean, you can play with that. So let me just stop at 10, which was looking good. So you can just copy this out and play with it. Find it on Facebook. I'm not able to put it on YouTube because of the sharp corners in the brackets for encoding. So with this, we come to the end of the Sturm-Liouville problem, and it's not really like a numerical thing, so to speak, but that's what we have, right? So that's what it is. That's the Sturm-Liouville problem. Let me see. Yeah, if you have not subscribed to this channel, please go ahead and do that right away. And of course, hit the notification bell so you can always get alerted each time a new video is released. And like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.